Alright, time for another draftphysics.com, debatephysics.com. But yes, no debaters really. Nobody capable of conversation regarding the elemental physics of our reality. Yes, I think it's all kind of elemental. So before I start reading any of the Wikipedia page, which is just technical jargon really, it doesn't really tell you anything about the nature of anything. What it's really doing, the physics, so heat is really probably should be a category. I'll have to figure out what to do with it exactly. And it really is just about the same idea that there's the small universe, okay, has elements in it, all right, and the elements are matter, okay, and what you could call elements of force. And that's the radiation kind of stuff, the stuff that flies from one place to another. Now you can force electrons and protons to move from one place to another, but they don't do it very effectively. But the force bits, stuff moving the speed of light, okay, that stuff does. And the trick with the matter, okay, is that it's in this form of atoms, that have a positive nucleus and then surrounding bits of electron. And in many substances, okay, especially ones that are not insulators that do transmit heat very well, the fact is that we can just make this a positive nucleus, and make these electrons, okay, so you get the idea, okay. And so when you push on an electron in stuff that's not an insulator, it sort of means that this stuff, these electrons can exchange positions and they can move. And the idea is when you're exchanging energy between them, the pressure, the movement transfers through all of them. So I've pointed out in like the case of electricity, the idea is you push them quickly and they're able to just jitter in the same direction. But if you push slowly, that is, you move them kind of slowly, it means they're going to bend a little this way, so they'll put a little pressure this way, they'll put some pressure on this electron this way, this electron will move over here. So you have a whole cascade of movement of the pressure. So that's the difference between high pressure, a quick jerk, and slow pressure. So it's sort of like breaking wood or some other kind of thing. The faster action has a different consequence than a slow action. And the same thing is for the internals of atoms. And the trick is all this motion. Say if I move this electron, it's a valence electron, whatever, it's being shared, and I move it. The fact is that there's a pressure that's going to say it was in an equalized position and it's going to go back again. And when it goes back again, it's going to overshoot, and then it's going to overshoot, and then it's going to overshoot. And so what you have in the electrons is they're very springy. So it's really hard to push them without them doing this afterwards. So it's a lot like a spring. A spring can push something and it always has to lose some of the energy because the last push just really doesn't work and it goes back to its relaxed position and then it springs back again, so it oscillates. So it has some of the energy gets stuck in the spring itself, and the fact that it can't give all of it, and so it has to come back. And when it comes back, obviously it can't give energy forward, so that energy is sort of lost and it ends up oscillating. Now if it was perfectly frictionless, that is, wasn't in any kind of atmosphere and it didn't have the capacity to convert the motion into heat in itself, it would oscillate theoretically forever. And the same is true for these electrons. There's absolutely no friction in this system. So any movement by one of them ends up being movement by all of them, and that is heat. Heat is the tension and how much wobble there still is in these electrons. And the only way to get it out is you have to dampen it out. That is, you have to have some system that it can give the pressure to, give the shaking that's happening. So something has to push in with less you push out with more energy than you push in with. So again, sort of like the Earth and the fact of its gravity. More comes in than goes out. Well, you need the other case to lose energy, to lose heat. You have to do the other case. But it's just really just about the fact that the electrons are doing the motion. So again, and you could talk about atoms turning. You could talk about, when you're changing the domains of a magnetic pole or something. You can think about that as a turn, but it might not be. But yes, the nucleus itself can also be moved and turned. So obviously when you move a whole object, you're moving nucleuses too. So as the electrons apply their pressure is applied to the nucleus itself, and it eventually moves. So if you have enough pressure on all the electrons, the nucleus has to be dragged along. So if you have a flow of energy in one direction, it will move the electrons first, and then the nucleuses will follow behind. They're also subjected to the same oscillating problem, in the sense that once you stop, everything's going to have to rebalance, and this one might have moved a little bit further than this one, and so this one's going to have to go back, and if it goes back, it's going to jitter a little, and it's going to wobble, and you have to dampen all of that wobble out of a system to make it cold again. Alright, so that's probably... So the idea is heat is just the fact that energy, when you apply energy to conductive systems, okay, the energy dissipates throughout the whole system. So some of it you're losing to that dissipation, and once it's in there, it's a little difficult to get it back out again, because you have a bunch of motion in directions, all kinds of directions that are stuck inside of here. They're not going out. They're stuck going in directions that aren't very productive. So it's sort of like water. In a more perfect world, you could understand that you could poke water, and if there wasn't a capacity to lose it to moving the atmosphere and doing all this other stuff, that the oscillations in the water could also be very frictionless, and they would be forever. Like you can see that in a swimming pool. You can agitate the swimming pool, and it takes a really long time to get rid of that energy. So it just keeps moving through the system, the motion, and it dissipates and becomes quieter and quieter. More and more of it oscillates the same, and eventually it acquires a resonant frequency, and then it slowly dies down by pushing on the atmosphere. But it takes a long time to get rid of a small amount of energy. I suppose that's a pretty good analogy. But it's really just the fact that you can't, an electron really can't move, okay, without likely going back to where it was. And in the going back process, it's always just like with gravity, it overshoots. It gains more velocity than it needs, and then it ends up going back, and it just oscillates. And that oscillation has to go through the whole system, and it finally has to be excreted in some form. And the form is that every time you push into a universe, you do a little bit of work, and every time the universe pushes on you, it does work on you. So, and you have to sort of balance it to the system eventually will equalize, you could argue. That the pressure on the outside will become the same as the pressure on the inside, but it can take a while because there's no friction on the interior system. There's no place for it to just disappear. It has to disappear as radiant energy. That is, it has to disappear by pushing on the universe and excreting its extra amount of motion, its extra pressure. And it's just the same as the other arguments. Heat moves just like pressure moves. It goes from high pressure, more movement, to less movement. You can't go from less movement to higher movement. Alright, I think that's probably enough of a beginning. I'm just trying to think of some other analogies. So you could think of it as you got a whole building full of pendulums, and you vibrate the building, and all the pendulums start swinging. And it takes a while for all of that energy to dissipate through all of the pendulums. And again, they will eventually synchronize, and they will eventually, push into the universe and lose a little tiny bit of energy to the universe, and therefore relax, and push the opposite way a little bit less, And eventually, through each one of those pushes, it will transfer more energy as long as there's less energy coming at it than it's producing. So eventually the oscillations will be pulled, the energy will be pulled back out. But again, it can take a very long time for all of those events to happen. And critical is the part of the internal part where if there's a bunch of stuff oscillating unevenly, it won't be able to produce more. It won't be able to get rid of its energy because it's going to be yinning while it's yanging. One part of it will be losing energy as one part is gaining energy. One part will look cold to the universe, another part will look hot. So the cold part will absorb more energy, and as the hot part is trying to get rid of energy. And so it becomes more efficient at transferring the energy when it starts producing some sort of consistent radiation, like infrared radiation, like at a specific frequency. Then it can get rid of the radiation. But the more chaotic it is, the harder it is for the internal energy to be lost, because from the universe's perspective, it looks hot and cold. It's a little bit of a complicated argument, but like I said, you can understand that, if I had a table with a bunch of pendulums, I just bump the table, everything starts moving, and it's going to take a while, especially if all the pendulums are on the same platforms too. If the pendulums are on pendulums, I got pendulums on a platform, and I have those so they can move. The whole platform can move. And then that whole platform is tied to the other platforms by strings that allow them to move. You can see that any noise in that system will just keep moving through the system, and it's going to be difficult for it to get to the external world. Yeah, that's probably enough of that. Alright, so I should also point out that the Angela Collier, or whatever her name was, evil physicist, she did a video on temperature, and she's getting into the subject of density and all of that stuff, and that just has to do with the material, right? So the amount of atoms it has and the number of electrons is really the key point, density, and how many electrons there are per square tiny little section. It's really going to decide how much heat something could store. So you can understand the electrons wobbling is really how it's storing the heat. And until the electrons quiet down, is when it can lose that heat. But it has to lose it to some mechanism that can take the heat. And so other atoms hitting you makes it easy to exchange it, because it's easy to push on an atom and give it a velocity. So if you have more stuff pushing out than pushing in, okay, an atom will hit, and its probability of gaining energy from your surface is higher than it losing energy to your surface. And so that's what you're trying to do, is so you're just exchanging the pressure inside of an atom with another atom, and its momentum is part of that exchange process. And so you're going to give it a little more bounce if you're hotter than it would have if you were colder. So it's all momentum in the end. It's all just matter moving. It's little pieces of matter moving, and they're going to exchange their movement. And they're just saying, well, what's the vehicle for the exchange? So you can have the vehicle for exchange can be with physical atoms, which means that the electron pressure is easy, okay, to make communication between the electrons. Or the universe itself, space, which is a lot harder, okay, to communicate with. The connection is much less, so it takes you longer to radiate the heat in a vacuum than it is to radiate the heat if a bunch of atoms are touching your surface and taking away the extra pressure, the extra vibration. Yeah. All right, so I haven't played her entire video, so I don't know if there's anything in it that means anything. Obviously, they all think it's about kinetic energy, so I guess that's the other real big point to make, is they're giving the electrons that are wobbling this fake energy based on the fact that the higher their velocity, that somehow you square that to define how much energy they have, and it's just not true. There's just momentum. So they get these exaggerated notions of how much energy is in the vibrating because of this stupid, wrong kinetic energy formula. So again, it just ruins. It has infected all of physics and destroyed it, frankly. Every subject gets infected by this wrong theory and creates just wrong answers. All right, so to the Wikipedia page. Yeah, hit the button. That looks like it. All right. All right, so in thermodynamics, so, it's physics. This is probably doesn't deserve a special category. It's about momentum, and so it's about movement of matter. The movement is in the form of chaotic jitters. Some stuff is going this way, some stuff is vibrating this way, everything's vibrating at different directions, and all of that non-directionality is hard to capture to do work. To do work, we usually need a force to be moving in one direction collectively. And if it's going in all kinds of directions, it's too useless because the push, this action ends up being destroyed by the opposite action, the rebound. In thermodynamics, heat is the thermal energy transferred between systems due to a temperature difference. Okay, so a temperature is just a way of measuring how much jitter, average jitter. So you're pulling some of it out. You take a thermometer, and what are you doing? You're sampling how much jitter is in something by taking some of it and giving it to your thermometer juice. So your thermometer juice absorbs the energy. It's in a stuck tube, and so it can only absorb it by showing it as a form of expansion. That obviously, if I create a bunch of, the atoms are very quiet, they're very small, and if I put a bunch of jitter in them, then they get a little bigger. And so the juice tends to expand. Most things do that, and it's because the energy is in the form of pressure, and the pressure is between the objects, and there's chaos in their function, and so they're swinging in positions, which means the atom has to expand to accept the fact that there's all this extra motion. So the connection between the electrons has to end up creating more net distance between each other because they're not consistently in one place. All right, in colloquial use, heat sometimes refers to thermal energy itself. So it's obviously just motion, it's momentum. Heat is a form of momentum, and the key point is heat is in all directions. It's because it's a vibration in the atom itself, and it's not easy to extract that in some productive way because of the chaos. Thermal energy is the kinetic energy, so this is where everything goes wrong. Okay, it's not kinetic energy. It's active energy, so if the word kinetic meant active energy, well, there you go. But unfortunately, it means some other kind of bullshit, 1/2 mv squared. Of vibrating and colliding atoms in a substance. So I'd argue that you can break it down to something simpler, that it's not really, that the atoms themselves are vibrating. It's that the pieces they're made of are vibrating, the electrons. They're oscillating. And it's their oscillation that makes the atom itself hot or cold. All right, an example of formal versus informal usage may be obtained from the right-hand photo, in which the metal bar is conducting heat. So, that's sort of another point where you just say, oh, come on, it's not really, the heat obviously is one end is hotter than the other end. And we know that it takes a while for the heat to move through all of the atoms of the metal bar. Now, if it was electricity, it would go through really quickly. So obviously, the metal bar is good at motion in certain directions. It'll pass it. Motion in other directions, it doesn't pass as well. So that's sort of an explanation for how it's a good conductor, but it's in some sense a poor conductor, because obviously one end can get a lot hotter and it takes a long time for the heat to migrate into the whole bar, but it will. Eventually the whole bar becomes a certain diluted, less temperature from its hot end to its cold end. But if the metal bar is considered a thermodynamic system, then the energy flowing within the heat bar is called internal energy, not heat. So it's always just the motion of little bits of matter and its momentum, and the momentum is in all directions, and it just takes a while for that incoherent motion to be exchanged. Because at any 1 minute, like I said, it's doing a lot of this. And so if you look at it when it's doing this, it looks cold. If you look at it when it's doing this, it looks really, really hot. So that's the catch of it, is that it's, it's really, you're seeing the vibration. You're seeing, I guess that's the only way to say it. You're seeing how agitated it is. You're not seeing, because it doesn't have a direction. All right. The hot metal bar is also transferring heat to its surroundings, right? And it's doing it in two ways. One way is the way it's communicating to the universe itself, that is creating infrared radiation. That is, it's changing the frequency of energy that comes into it, and it's pushing on that with its electrons and giving it a more compressed frequency. And so that's why it starts to glow, is because it's taking the normal energy that's coming into it and it's increasing its frequency by pushing out, compressing it. And so it's creating higher and higher frequencies of reflections to the universe. And at the same time, by doing that, by forcing those compressions, that's a form of work. So it's losing some of its energy to compress the energy in the field, to increase the frequency of the reflection. It's doing a little bit of work. So it dissipates its heat by increasing the frequency of the radiation, the compression in space of the radiation. So instead of the radiation being 10 dots in this much space, by the electron pushing out, it changed it into 10 dots in this much space. And we can see that frequency. We can't see this frequency, but we can see this one. All right. The hot metal bar is also surroundings, a correct statement for both the strict and loose meaning of heat. So, hot metal is also transferring heat to its surroundings. A correct statement for both the strict and loose meaning of heat. That's hardly a strict definition, or exact or complete. So that's just hyperbole. This is a good enough definition. No, it's really not a good enough definition. Another example of informal usage is the term heat constant. I don't know, heat content. All right, so then you're just talking about, then you get into the density, the fact that heavy objects can hold more heat than light objects. Used despite the fact that physics defines heat as energy transfer. So heat is a condition that something's in, and it doesn't have to transfer it for it itself to be hot. So, it's like a spark can be really hot, 2,000 degrees in its tiny little space. How much of that energy is actually transferred, right? When a lightning bolt hits the ground, a tiny percentage is transferred to the atmosphere. The substance of the energy goes into the ground. So, eventually all the heat ends up dissipating, usually through some mechanism, because, again, if the universe is colder than the object, then the object will heat the universe a little bit, but it takes a really long time for it to dissipate the heat in that manner because of the nature of oscillations. More accurately, it is the thermal energy that is contained in the system or body. So again, thermal energy is just momentum. It's the momentum that's in the electrons, and you could argue the nucleus is also, that everything's moving. And you're just saying that that movement represents a certain amount of momentum. And that if you could get rid of that motion and move it into something else, you could make something move in a straight line. If you could convert all the motion in all directions and convert it into a more useful, like a laser beam. If you collect the energy and force it into one outlet, like the nozzle on a rocket. All right. As it is stored in the microscopic degrees of freedom of the modes of vibration. So it's modes don't matter. The word vibration is all you need. So the modes of vibration just have something to do with how easy it is to get rid of the energy. The less chaos, the easier it is to convert it into some other form of motion. But the fact is that it's the degrees of freedom don't have it. It's either moving or not moving. The motion is momentum, and you're just saying it's easier to transfer the momentum in some conditions than in other conditions. All right, heat is energy in transfer. So no, it isn't. Okay, so heat is a condition of an atom. An atom has a temperature, and the temperature is decided by how much jitter, how much redundant motion, trapped motion there is in its electrons and protons and nucleus. All right, heat is energy in transfer to or from a thermodynamic system by a mechanism that involves the microscopic atom modes of motion or the corresponding macroscopic properties. So this isn't saying anything, right? I mean, that's just mush. This descriptive characterization excludes the transfer of energy by thermodynamic work. So this doesn't even mean anything either. Obviously, every time you see a transfer, you can call that work, because you're working, one thing is working on the other, in the sense that one thing is causing the other thing to have what it had, and it worked on it to do that. But work doesn't necessarily involve the destruction of energy or the termination of energy, because you can never get rid of the energy. So the heat always is going somewhere else. It never ends somewhere. You can't just say, okay, this is where the heat stops. This is where motion stops. It's just about spreading the motion to some other system. So again, we radiate energy to the whole universe, and we can heat the whole universe, theoretically. And so that heat is still moving around, and then the whole universe could heat us. All right. Is one of the principal processes by which thermodynamic systems can interact with the surroundings and exchange energy. So it's just a visible exchange. That's what we call work. And the invisible exchanges we don't acknowledge. I don't know, something like that. This exchange results in an externally measurable microscopic forces on the system surrounding. Yes, so that's the whole thing, this word measurable. So there's circumstances where we can measure it, and there's circumstances where we can't measure it, but we really should have just acknowledged that the unmeasured ones are just as real work-wise as the measured ones. Defined quantitatively, the heat involved in a process is the difference in the internal energy, so the momentum, between the final and initial states of a system. So again, the system can't lose energy if it isn't connected to another system. So there's no point in talking about the internal state of a system changing, because it can't change unless it interacts with another system. All right, and subtracting the work done in the process. So there's no work done inside a system, so that's just like any other momentum argument, that a closed system, the energy has to stay constant in the system. And heat stays the same if there isn't some other system for the object to interact with. This is the formulation for the first law of thermodynamics. So as stated here, it says, the first law of thermodynamics is a formulation of the law of conservation of energy in the context of thermodynamic process. So we know it's the conservation of motion in the universe, and there's no way to get rid of the motion. So the force is the stuff moving at the speed of light. the force can act on you and cause your matter to move at a slower speed. Then your matter moving at a slower speed can interact with the universe and cause the force not to move at a higher speed, but to compress the content in the field, and therefore give it properties that enable it to do different things than it would do if it was at a lower frequency. But it's the same momentum. It's the same number of people pushing on a door. It's just that you can have them all push at the same time, or you can have them push at different times, and the outcome will be different depending on how you consolidate their pushing force. The more consolidated the pushing force, the more work it can do. The more immediate, time-dependent work. The faster you can move the energy from yourself to the thing, the more organized the energy is, the easier it is to transfer it. But it's always just, again, every bit of motion is never, there's no termination. It always has to keep moving from one system into another system, into another system, into another system. It's always in a system somewhere that modify a thermodynamic systems, well, blah, 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 blah. So the idea that you have to conserve momentum covers the idea, or the conservation of energy covers this thermodynamic first law. So it's just a reiteration of the fact that you have to conserve motion. All right. Calorimetry is measurement of quantity of energy transferred as heat by its effect on the state of interacting bodies. For example, by the amount of ice melted, or by a change in the temperature of a body. So you're just measuring how fast you're extracting energy, and how much motion or vibration you're pulling out of something, blah, blah, blah. But you don't need the whole category for that, because it's exactly the same in a sense. It's just the smaller pieces of energy, but it's all the same thing. It's just matter moving or force moving. Stuff is either moving the speed, there's either energy in the form of stuff moving the speed of light, or there's matter that has stuff moving the speed of light pushing it. And so there's always that momentum in the system somewhere. So if there's more force pushing matter, there's less force free. All right, in the international system of units, the unit of measurement of heat is a form of energy, is the joule. So again, this is, in my opinion, these assignments of these words don't mean much because they have way too many of them. So a watt is the same as a joule, all right? And then you can convert newtons into joules, and it's just, they shouldn't have all of these different definitions for the elemental quantity of a bit of energy. So I would vote for just using watts. Because we can see wattage all the time in our life. We can see how much watts it takes to run the phone, or to do this, or to heat a room, or to do, we can see it so plainly that it's a much better definition of a unit of energy. All right. As a form of energy, heat has a unit joule in the international system of units. In addition, many applied branches of engineering use other traditional units, such as the British thermal unit, BTU, all right, which again you can sort of make relative comparisons, but it's not a very good absolute figure. And the calorie, and again that's the limitation of the calorie is that we think of it in terms of an amount, but we're always thinking of calories in terms of how much we get out of it. So you could eat a 1,500 calorie Big Mac, and because your body says this is junk food, it gets rid of it before it pulls much out of it. So you might only get 300 calories. In the inverse, you could eat a 500 calorie potato, and your system could say, we like this, and it'll get 400 watts out of the 500 watt potato. All right, anyway. The standard unit of rate of heating is the watt. Okay, so we like that, defined as 1 joule per second. Anyway, the symbol Q for heat was introduced, so Q is a pretty bad symbol, by Rudolf Cellulus and whatever, some other Renke guy. I wonder if that's the, yeah, that might be him, the guy who invented the word for radiation. No, he's a mathematician. All right. Heat released by a system into the surroundings is by convention a negative quantity. So you're losing your heat. So, and something else is gaining it. So which way you call it, really doesn't matter. When a system absorbs heat from the surrounding, it's a positive Q. Heat transfer rate, or heat flow per unit time, is denoted as Q, but it is not a time derivative of a function of state. Well, everything is, frankly, a time derivative. So everything is about how long you're exposed to a pressure, which can also be written with the dot notation, since heat is not a function of state. Heat flux, whatever that is defined as the rate of heat transfer per unit cross-sectional area, watts per square meter. Well, there's very few surfaces, there's very few things that expend watts per square meter, obviously. So they're just saying watts per the density of the substance, maybe. But I mean, obviously, surface is where you usually radiate. You usually transfer your heat by contact, and the contact usually isn't immersive. So like even if I dumped you in water, you would start losing your heat to the water, and you're going to lose it over your surface area. You're not going to really lose it per square meter. You're going to lose it per square inch of contact. All right, anyway, heat and entropy. This probably won't be any fun. In 1856, Rudolf Cellulus, I guess that is, referred to closed systems in which transfer of matter do not occur. So it's not really, you don't have to transfer matter to still be connected systems. So if you're radiating, you're throwing, force at each other all the time. So you're capable of transferring your condition to something else through the force itself. Define the second fundamental theorem, the second law of thermodynamics. So let's read that one. The second law is a physical law based on universal empirical observation concerning heat and energy interconversions. A simple statement of the law is that heat always flows spontaneously. Now, why would somebody say that? I mean, that's just a terrible word. It always transfers conditionally from hotter to colder regions. So this is just the simple pressure argument. Faster things give velocity to slower things. Slower things don't give velocity to faster things. Obviously. Slow things can't catch up to fast things, therefore they can't push them. Fast things can catch up to slow things, therefore they can push them. All right. If two transformations which, without necessitating any other permanent change, can mutually replace one another, it's called equivalent. Then the generations of the quantity of heat Q from work at temperature T has the equivalent value. So that is saying you have a quantity of heat Q, and then you have T, which is the temperature. I don't know. You really can't divide temperature into heat, but whatever. In 1865, he came to define the entropy symbolized by S, such that due to the supply of the amount of heat Q at temperature T, the entropy of the system is increased. So now the simple statement is he's saying the temperature is just a measure of your relative condition, and that you have to, if you have less heat than the temperature, you'll move one way. If it's more heat than the temperature, okay, so if the temperature Q is higher than the temperature something else, it's really not very clear. I mean, this is really bad formalization, in my opinion. All right, in a transfer of energies, and that's what it is. It's a transfer. So these things should be assigned object 1, object 2. And all you're really just, I mean, it's just that simple. You can only transfer energy productively in a positive direction or in a negative direction based on this fraction if you're just comparing the temperature of one object to the temperature of another object. And you know it has to go one way. In a transfer of energy as heat without work being done. All right, so work being done, it's clearly the transfer is the same as doing work, and work doesn't use energy. It's just using the energy temporarily, converting it still again from one thing to another thing to another thing. So you're just taking motion. The motion in the wire is real. The motion in the motor is real. Then the motion created by the motor is real. That motion agitates the environment in some way. It's just a place where it's all moving. And to call one place work and to say the other stuff isn't work would be kind of silly. So anytime you convert energy from one circumstance to another circumstance, you're technically doing work. But you're not using anything's energy up. You're just using one form of motion. If you could keep that motion running, like a stream, in the water wheel, then you can keep pulling energy out of the system because the system keeps supplying new energy for you to pull. There are changes in entropy in both the surroundings which lose heat and the system which gains it. The increase, delta S, of entropy in the system may be considered to consist of two parts. An increment, delta S, that matches or compensates the change. Delta minus delta S, the entropy of the surroundings, and further. So you're just, again, this is just a conservation law. All right, that you can't, whatever you lose is a real substance in somebody else's pocket. It's all real money. You can't get rid of the money. All you can do is exchange the money. You give away $5, you're $5 poorer. It's really not that complicated. All right, for a closed system, i.e. a system from which no matter can enter or exit. So again, it doesn't matter whether matter can enter or exit. If you were a single object in the universe, the universe still has force in it, you could argue, then you're still going to be able to dissipate whatever your temperature is to the universe, and you're going to lose it all, depending on how big the universe is and how much force is in it. One version of the first law of thermodynamics states that the change in internal energy of a system is equal to the amount of heat supplied to the system minus the amount of thermodynamic work. So again, they're just playing word games. There's the heat you can see transferred and the heat you don't see. The stuff you can call useful, and then the stuff that's, not doing any productive work done by the system on the surroundings. The surroundings will always be affected. And so again, if I put a bunch of motion in matter, then the universe is colder. And if I take out the motion in that matter, the universe is hotter. All right, the foregoing sign convention for work is used in the present article, but an alternative sign convention followed by IUPCA, whatever, for work is considered the work performed on a system by its surroundings as positive. This is the convention adopted by modern textbooks for physical chemistry, such as those of Peter Atkins. So again, we have to believe these are people who are going to tell us what the truth is. But many textbooks on physics define work as work done by the system. So whatever. Yeah, we won't bother with all this. I would just argue these are not great formalizations. And certainly when they start imposing the mv squared part is when it's really going to get ugly. All right. So, again, all you're doing is saying there's momentum in little tiny objects, and then there's momentum in big objects. And it's all the same momentum. It's just motion of a bit of mass. And that stuff has to be essentially conserved either in a, like I said, either you're liberating a piece of force, or the piece of force is pushing a piece of matter. Those are the only two conditions the force can be in. And if it's liberated, then the free force has more pressure, and if it's being used, then the free force has less pressure. All right. As a common noun, English heat, warmth, just a French chandelier, German blah blah, Latin color, Greek blah blah, who refers to the human perception of. All right, so yeah, so there's this other way of using it, the lazy word for heat, which is warmth or something like that. Either thermal energy or temperature. So again, thermal energy has to really, it's the same as temperature. You can't really say thermal energy is something different than temperature. Speculation on thermal energy or heat as a separate form of matter has a long history, identified as caloric and whatever this is theory and fire. So yeah, they had lots of bad ideas about how, electricity was a fluid. Lots of things have been a fluid or a substance, and heat isn't a substance in one sense, but in one sense it is something that you collect. You collect units of force in the universe, and that's how an electron can move, is it's collected units of force. And while it's collected those units of force, the electron is moving slower than the force would have moved if the force was free. So clearly in one form, the force has a different function when it's pushing matter versus its function when it's free to acquire a new thing to push. Heat has been discussed in ordinary language by philosophers. For example, this 1720 quote from John Locke. Okay, heat is a very brisk agitation of the insensible parts of an object. So that's a reasonable enough argument. And so it's like a bunch of springs vibrating, and there's no internal friction. So the springs just keep vibrating until you find some way to push on them and take away the energy, have them push on some external substance. And the only external substance can either be an atmosphere, or the other substance can be the universe itself, which is constantly bombarding you with what we call electromagnetic radiation, what is just little bits of force that you reflect, which produces in us that sensation from whence we these should be real words. Denominate the object hot. So what in our sensation is heat? So what in our sensation is heat? I mean, this isn't a good sentence. In the object is nothing. Oh, well, this is from Locke, so obviously this is 1700 talk. In the object is nothing but motion. There you go. All right, so it's momentum. That's the truth of it. The heat is being stored in the motion of electrons. This appears, by the way, whereby heat is produced for we to see that the rubbing of a brass nail upon a board will make it very hot. And the axle trees of carts and coaches are often hot, and sometimes to a degree that it sets them on fire by the rubbing of the nave of the wheel upon it. Okay, so yes, friction can cause a lot of heat, and the heat is motion, useless vibration, in the sense of useless in the sense that it's not going in a direction, and so it's just chaos, motion. All right, this source was repeatedly quoted by Joule, John Tyndall's Heat Conserved as a Mode of Motion, was instrumental in popularizing the idea that heat as motion to the English-speaking public. So again, this is like the 1800s. They sort of formalized this idea that heat is just like any other form of energy. So if you're making heat, you're losing energy. And so instead of being thought of as some separate event that took place, it was better understood that you're losing energy to make heat. That if you're using your momentum, you have to expend momentum to make heat. The theory was developed in academic publications in French, English, and German from an early time. The French technical term called, I don't know, used by Carnot was taken as equivalent to the English heat and German Warmth, while the equivalent heat would be German Hitze. So, where the stupid words come from. All right, so maybe we'll try this. Classical thermodynamics. We'll see what happens here. In modern understanding of heat, it's often partly attributed to Thomson's 1798 mechanical theory of heat, concerning the source of heat which is excited by friction, postulating a mechanical equivalent of heat. So obviously the mechanical equivalent is its motion of electrons, and it's just that they're moving back and forth, which isn't terribly useful. In the history of science, the mechanical equivalent of heat states that motion and heat are mutually interchangeable in that in every case, given amount of work would generate the same amount of heat provided the work done. So this is where essentially the joule thing comes in too, where they all decided to understand that if they could possibly convert all of something's motion into heat and then measure the heat, they could measure how much total motion or energy the thing had have. So you could measure how much energy something has by converting all of its energy into the heating of some material, and based on how dense the material is and all that kind of stuff, you could figure out how much energy you would actually exchanged from one thing into another thing. A collaboration between Nicholas blah blah and Sadi blah 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 in the 1820s had some related thinking along similar lines. All right, Julius Robert Mayer, frictionally generated heat in paper pulp and measured the temperature rise. Okay, so now we're getting close to Joule. In 1845, Joule published a paper entitled The Mechanical Equivalent of Heat. Okay, so it probably would have been better to say that heat is the mechanical equivalent of momentum. Okay, in which he specified a numerical value for the amount of mechanical work required to produce a unit of heat. So this is the unit of heat, is the watt, is the joule, here we're just saying this is what we're going to call a certain amount of motion in the universe, based on heat production by friction in the passage of electricity through a resistor and in the rotation of a paddle in a vat of water. Now there was no problem with his resistor experiments, but his paddle wheel experiments were broken by the fact that they still believed in this living force crap. So what he did was drop things in gravity with a string attached to them. And the fact is the slower you drop something, just like the slower you lift something, the more work it is. The more time gravity is pushing on the object, the slower you can make it fall, the more time gravity is pushing on it. And so the more gravity you're collecting. So that's where the mv squared thing came in, is that they are assuming that because they dropped something the same distance, that it was the same energy. And you didn't collect the same energy. If you drop it slowly, you collect more energy. So if I drop a ball bearing down a staircase, I create 4 units of 9.8. But if I just drop it from the distance, I only get 2 units of 9.8. Only 2 units of time. So if you can extend the time that something falls over, you're extending the amount of time the force pushed on it. So therefore you're collecting more energy. And that's why they ended up with this silly notion that there's a squared v. 1/2 mv squared worked. And it only worked because they didn't understand that when you drop something slowly in gravity, you're going to apply more gravitational energy to the object, and therefore you can collect more energy from the object's fall. Just a fact. You can get more energy out of something by dropping it down a staircase, because it'll take it longer to fall. All right, the modern understanding of heat is often partly attributed, so we probably don't need this part. Let's see what it says. Postulating a mechanical equivalent of heat. Okay, I already read that. That's why I said we don't need that. All right, so that's probably enough for now. I made my point that, okay, heat is, the physicists are conceding that heat is just another form of momentum, motion, and that it's all quite measurable if you can put it in the right container, if you can put it in the right body. And I'm just going to make the counter argument again that they've ruined the assignment of that unit, because they think the unit is based on distance and they don't think it's based on time. So they think an amount of pressure is some sort of, how much if something moves, rather than how long something's applying the pressure. Some kind of example like that. But my simple description would be that gravity is like rain, and you're collecting it in a piece of matter. And obviously the longer the matter can collect the rain, the longer the time you're allowing it to take to fall, so you don't allow it to acquire any velocity. So if you don't allow it to keep its velocity, you can collect more energy from the source than if you let it free fall. If you let it free fall, then it acquires a velocity and it gets out of the gravity quicker. So it's really just about a unit of time, tells you how much rain is hitting something. And if you want to pull the rain out of that object, you can pull more rain out of an object you drop slower than you can pull out of an object you dropped quickly. Yeah, I think that'll do. All right, so till the next time and such. Obviously, Wikipedia is evil and stupid. This, is just a bunch of chaotic mush. It really doesn't get to any kind of elemental description of any physics here. There's no description. They don't even say the word force in this thing anywhere. Any kind of recognition that that you can transfer heat, in forms of energy that's moving the speed of light, radiation, or you can transfer it by just pushing a piece of clay against the surface and taking away some of the heat. Anyway, till the next time and such.